Welcome back to Lesson 6 in our study of the network layer of the TCP/IP model for the course Networks and Distributed Systems, based on the textbook by Jim Caros and Keith Ross, Computer Networking, a Top-Down Approach. In the last lesson, we talked about the issue of fragmentation in the network layer. In this lesson, we're going to pick up on addressing, so let's go ahead and pick up where we left off. Now we'll look at IPv4 addressing. A host typically has only a single link into the network. When IP in the host wants to send a datagram, it does so over this link. The boundary between the host and the physical link is called an interface. Now consider a router with its interfaces, because a router's job is to receive a datagram on one link and forward the datagram on some other link. A router necessarily has two or more links to which it is connected. The boundary between the router and any one of its links is also called an interface. A router, therefore, has multiple interfaces, one for each of its links. Because every host and every router can send and receive IP datagrams, IP, the Internet Protocol, requires each host and router interface to have its own IP address. So an IP address is technically associated with an interface rather than a host or a router containing that interface. Each IP address is 32 bits long, or 4 bytes, and there are about 4 billion possible IP addresses. These addresses are typically written in dotted decimal notation, in which each byte of the address is written in decimal form, not binary, and is separated by a period or a dot from other bytes in the address. For example, the IP address 193.32.216.9, the 193 is the decimal equivalent of the first 8 bits of the address, the 32-bit decimal equivalent of the second 8 bits of the address, and so on. Therefore, the address 193.32.216.9 in binary notation is as you see it here. 111.000.001, that's the first byte. 001.000.000, byte 2. 110.110.000, byte 3. And 00001.0, oh, excuse me, 00001.001. And if you remember your binary to decimal conversion process from your introductory course in computers, you should be able to evaluate each of those 4 bytes and see how it turns into that decimal number up above. Each interface on every host and router in the global internet must have an IP address that is globally unique. That is, except for those interfaces that are behind NATs, Network Address Translators, which we'll talk about later. A portion of the interface's IP address will be determined by the subnet to which it is connected. This figure shows an example of IP addressing in interfaces. One router with 3 interfaces is used to interconnect 7 hosts. Take a look at the IP addresses assigned to the host and router interfaces. The 3 hosts in the upper left portion and the router interface to which they are connected all have IP addresses of the form 223.1.1. something. That is, they all have the same leftmost 24 bits in their IP address. The four interfaces are also interconnected to each other by a network that contains no routers. This is a switch. This is not a router. And so these three hosts are connected together by this switch, and the switch is connected to the router. What you should also note is that the switch does not have an IP address. This network could be interconnected by an Ethernet LAN, local area network, in which case the interfaces would be interconnected by an Ethernet switch, which is what this is. This network could be interconnected by an Ethernet LAN, in which case the interfaces would be interconnected by an Ethernet switch or by a wireless access point, as we can see from these two small networks here. Ethernet switch, wireless access point. We'll ignore that switch for the time being. It is not a host, it is not a router, it is not required to have an IP address. Although they could, but it's not required to have one. In IP terms, this network interconnecting three host interfaces and one router interface forms a subnet. IP addressing assigns an address to this subnet of 223.1.1.0/24, where the /24 notation, sometimes known as a subnet mask, indicates that the leftmost 24 bits of this 32-bit quantity define the subnet address. The subnet 223.1.1.0/24 therefore consists of three host interfaces: 223.1.1.1, 223.1.1.2, and 223.1.1.3, and one router interface, 223.1.1.4. Any additional host attached to the 223.1.1.0/24 subnet would be required to have an address in the form of 223.1.1.4 to 255, somewhere in that range. So the last octet or the last byte would be anywhere from 4 to 255. There are two additional subnets shown. There's the 223.1.2.0/24 network and the 223.1.3.0/24 subnet. The IP definition of a subnet is not restricted to Ethernet segments that connect multiple hosts to a router interface. To get some insight here, consider this figure, which shows three routers that are interconnected with each other by point-to-point links. Each router has three interfaces, one for each point-to-point link, and one for the broadcast link that directly connects the router to a pair of hosts. What subnets are present here? Three subnets: 223.1.0/24 right here, 223.1.2.0/24 right here, and 223.1.3.0, which is this subnet right here. But note that there are three additional subnets in this example: 223.1.9.0/24 for the interfaces that connect router 1 and router 2 right here, 223.1.8.0/24 for the interfaces that connect routers 2 and 3 right here, and 223.1.7.0/24 for the interfaces that connect router 3 to router 1. For a general interconnected system of routers and hosts, we can use the following recipe to define the subnets in the system. To determine the subnets, detach each interface from its host or router, creating islands of isolated networks with interfaces terminating the endpoints of the isolated networks. Each of these isolated networks is called a subnet. If we apply this procedure to the interconnected system in this figure, we get 6 islands or subnets: 223.1.1, 223.1.9, 223.1.7, 223.1.8, 223.1.2, and 223.1.3. From the discussion above, it's clear that an organization with multiple Ethernet segments and point-to-point links will have multiple subnets, with all of the devices on a given subnet having the same subnet address. In principle, the different subnets could have quite different subnet addresses. In practice, however, their subnet addresses often have a lot in common. To understand why, let's next turn our attention to how Internet addressing is handled in the global Internet. But before we do that, let's take a break. I want you to study your notes on this video and be sure to fill in the information in your study guide, because this is important information and you need to understand how it works. When you get done, come on back and we will see how it's handled on the Internet.